In 1996, General Motors introduced the EV1, one of the world's first modern electric cars. It accelerated from 0 to 60 miles per hour in about 8 seconds, delivered more than 100 miles of driving range in later versions, and inspired thousands of loyal drivers. Yet the program ended after only a few years, and nearly every leased vehicle was reclaimed. The reasons remain debated to this day, but one thing is certain: the electric vehicle market that exists in 2026 looks very different from what many people expected 3 decades ago. Fast forward 30 years, and the competition has completely changed. The global EV market now exceeds 17 million vehicles sold annually. Battery production has climbed beyond 1 terawatt hour per year, and governments and manufacturers have committed well over $1 trillion toward electrification. Yet, despite those enormous investments, the biggest breakthrough may not be another electric car. It may not even be another battery chemistry. Instead, it could come from changing the way batteries are manufactured. For years, the conversation has focused on range, charging speed, and horsepower. Companies competed over who could travel 500 miles, charge in 15 minutes, or accelerate from 0 to 60 miles per hour in under 3 seconds. But behind every headline-grabbing vehicle sits a battery factory costing anywhere from $4 billion to $8 billion, filled with equipment that follows a manufacturing process largely unchanged for decades. Tesla believes that process can be reinvented. The technology attracting so much attention isn't simply a new battery cell. It's the company's work on dry electrode manufacturing, a process accelerated after Tesla acquired Maxwell Technologies for approximately $218 million in 2019, rather than relying on traditional liquid slurries and massive drying ovens. The goal is to manufacture electrodes with far fewer energy-intensive steps. If successfully scaled to mass production, Tesla has said the approach could reduce factory complexity, lower energy use, and simplify future battery plants. To understand why that matters, you first need to understand how nearly every lithium-ion battery is made today. Across the world, manufacturers begin by mixing active materials, conductive carbon, binders, and chemical solvents into a thick slurry. That mixture is coated onto copper and aluminum foil before passing through industrial drying ovens that can stretch 100 to 200 meters in length. Those ovens operate continuously, consuming significant amounts of electricity while evaporating solvents that must later be recovered through expensive environmental systems. Industry studies estimate that electrode coating and drying account for roughly 20% to 30% of battery manufacturing costs and occupy nearly 1/3 of a typical battery factory's production floor. In a 40 gigawatt hour gigafactory producing batteries for hundreds of thousands of vehicles annually, even small improvements in manufacturing efficiency can save hundreds of millions of dollars over the life of the facility. Tesla's dry electrode process aims to remove much of that complexity. Instead of creating a liquid slurry, specially engineered powder materials are compressed directly onto the current collector, eliminating the need for large solvent-based drying operations. Although researchers have explored this concept for years, producing millions of high-quality battery cells consistently has remained one of the industry's biggest engineering challenges. If those challenges can be overcome, the implications extend well beyond Tesla. Battery packs still account for roughly 30% to 40% of an electric vehicle's manufacturing cost. Reducing battery costs by only $10 per kilowatt hour can save roughly $750 on a typical 75 kilowatt hour battery pack. Multiply that across 2 million vehicles and the savings approach $1.5 billion. At industry scale, even incremental manufacturing improvements become enormously valuable. That explains why companies around the world are investing so heavily in battery innovation. China remains the world's largest battery manufacturing hub, producing roughly 75% to 80% of global lithium-ion cells, while companies in the United States, Europe, Japan, and South Korea continue investing billions in next-generation factories. If a manufacturing breakthrough significantly reduces production costs or factory complexity, competitors everywhere, not just in one country, would feel pressure to adapt. The next phase of the EV race may therefore be less about who invents the next battery chemistry and more about who perfects the next generation of manufacturing. History has repeatedly shown that companies capable of building products faster, more efficiently, and at lower cost often reshape entire industries. And that may be the real story unfolding today, not a battle over one battery or one vehicle, but a race to redefine how millions of batteries are built. If dry electrode manufacturing reaches its full potential, the biggest innovation of the decade may not be something drivers experience behind the wheel. It may be something that happens inside the factory long before the car ever reaches the road. For decades, battery engineers have chased one number above all others: cost per kilowatt hour. In 2010, lithium-ion battery packs cost well over $1,100 per kilowatt hour. By 2020, that figure had fallen to around $140 per kilowatt hour for industry averages. And by the mid-2020s, leading manufacturers had pushed costs even lower through larger factories, better chemistry, and higher production volumes. That dramatic decline is one of the biggest reasons electric vehicles have become mainstream. But engineers are now discovering a difficult truth: squeezing another 5% or 10% out of the same manufacturing process is becoming increasingly expensive. That's why Tesla appears to be targeting the factory rather than just the battery. Think about what happens inside a modern gigafactory. Before a single battery cell powers a car, thousands of tons of raw materials move through mixers, coaters, drying ovens, rollers, slitters, and inspection systems. A single battery plant can contain hundreds of robots, operate 24 hours a day, and produce enough cells every year to power 500,000 to 1 million electric vehicles. Yet one of the slowest stages in that entire process is still drying the electrode coating. Traditional manufacturing requires liquid solvents to hold battery materials together during coating. After the mixture is applied, enormous ovens heat the electrodes for several minutes before the remaining solvent is recovered through complex recycling equipment. Those ovens consume significant energy, occupy vast factory space, and require constant monitoring to maintain consistent quality. Tesla's dry electrode approach is designed to bypass much of that process. Instead of depending on liquid solvents, the materials are engineered to bond together in a dry form before being compressed onto the metal current collector. In theory, that means fewer machines, fewer production stages, lower energy consumption, and shorter manufacturing lines. According to Tesla's long-term manufacturing goals, the technology could significantly reduce factory footprint while simplifying production. Reaching those goals consistently at industrial scale remains a major engineering challenge, but the potential rewards explain why so much research has gone into the process. The timing couldn't be more important. Global demand for batteries continues to grow at an extraordinary pace. Industry forecasts suggest annual battery demand could climb from roughly 1 terawatt hour today to more than 5 terawatt hours during the next decade as electric vehicles, commercial trucks, grid storage, and renewable energy systems expand worldwide. Meeting that demand will require hundreds of new battery factories, representing investments measured in the hundreds of billions of dollars. Now imagine reducing the construction cost of each future factory by even 10%. If a gigafactory costs $6 billion, that's approximately $600 million saved before production even begins. Multiply that across 20, 30, or even 50 future facilities, and the savings become enormous. Suddenly, manufacturing innovation becomes just as valuable as battery chemistry itself. This is why the competition has become so intense. It's no longer enough to produce the best battery. Companies must also produce it faster, with fewer manufacturing steps, lower energy consumption, and higher production yields. Even a small improvement in yield, raising production efficiency from 95% to 98%, for example, can translate into millions of additional battery cells every year without building another factory. That may not sound exciting compared to headlines about faster charging or longer range, but inside the industry, these manufacturing gains are often worth far more than a few extra miles of driving distance. Because in the end, the company that learns how to build batteries more efficiently doesn't just reduce cost. It gains the ability to scale faster than everyone else. And in a market expected to produce tens of millions of electric vehicles every year, scale can become the biggest competitive advantage of all. One question immediately comes to mind. If dry electrode manufacturing has the potential to reduce costs, simplify production, and reshape battery factories, why hasn't every major battery company already adopted it? After all, companies like CATL, BYD, Panasonic, LG Energy Solution, and Samsung SDI employ tens of thousands of engineers and invest tens of billions of dollars every year into battery research. The answer lies in the enormous difference between proving an idea in a laboratory and producing millions of battery cells with consistent quality. Manufacturing experts often say that inventing a technology is only the first 10% of the challenge. The remaining 90% is figuring out how to build it reliably every minute of every day without sacrificing quality, safety, or profitability. Battery manufacturing operates under incredibly tight tolerances. A modern electric vehicle battery pack may contain anywhere from 800 to more than 4,000 individual cells, depending on the design, and every one of those cells must perform almost identically. If even a tiny percentage develops defects, the financial consequences become enormous. Imagine producing 100 million battery cells each year with a 99% production yield. That sounds exceptional, yet the remaining 1% still represents 1 million defective cells. Those cells cannot simply be installed into vehicles. They must be inspected, recycled, or discarded, turning what appears to be a tiny manufacturing imperfection into losses worth hundreds of millions of dollars. This is why battery companies obsess over production yield as much as battery chemistry itself. Dry electrode production makes that challenge even more demanding. Traditional wet electrode manufacturing uses liquid solvents that help distribute active materials evenly across extremely thin metal foils. Remove those solvents, and engineers must find entirely new ways to ensure every microscopic particle bonds together with remarkable consistency. Even differences measured in just a few microns can affect electrical resistance, charging behavior, heat generation, and long-term battery durability. Solving those problems isn't simply a chemistry challenge. It requires advances in material science, precision engineering, robotics, quality control, and high-speed automation operating together on production lines capable of manufacturing millions of cells every month. This is one reason Tesla's acquisition of Maxwell Technologies in 2019 attracted so much attention throughout the battery industry. The approximately $218 million purchase wasn't just about patents. It gave Tesla access to years of research into dry electrode processing while allowing its engineers to integrate that work directly into future manufacturing systems. Since then, industry observers have closely followed Tesla's efforts to scale the technology because the real breakthrough isn't demonstrating that dry electrodes can work. The real breakthrough is producing them consistently at automotive volumes while maintaining high yields, long cycle life, and competitive costs. That distinction is what separates laboratory success from industrial leadership. History is filled with technologies that worked perfectly during small-scale demonstrations, but failed once manufacturers attempted to produce millions of units. The companies that ultimately reshape entire industries are rarely those with the most exciting prototype. They are the ones capable of transforming a scientific idea into a reliable manufacturing process that operates every hour of every day with minimal waste and consistent quality. In the battery industry, where future demand is expected to reach several terawatt hours annually, solving that manufacturing puzzle may prove even more valuable than discovering the next breakthrough battery chemistry itself. If Tesla succeeds in solving that manufacturing puzzle, the effects won't stop at its own factories. They could ripple across the entire battery industry, forcing competitors to rethink billions of dollars worth of future investments. That's because battery manufacturing isn't something companies can redesign in a few months. A modern gigafactory typically takes 2 to 4 years to plan, construct, equip, and ramp up to full production. By the time a factory opens, much of its technology has already been locked in years earlier. If a fundamentally more efficient manufacturing method emerges after those decisions have been made, companies face an uncomfortable reality: continue operating older production lines or spend billions upgrading facilities that are still relatively new. This is why battery manufacturing has quietly become one of the most important competitive battlegrounds in the automotive industry. Over the past decade, manufacturers have focused heavily on expanding capacity. China built the world's largest battery ecosystem, producing roughly 75% to 80% of global lithium-ion cells, while also leading in cathode materials, anode processing, and battery-grade graphite. Companies such as CATL and BYD invested aggressively in scale, allowing them to supply batteries to automakers around the world. Their advantage wasn't based on a single invention. It came from years of investment, enormous production volumes, and highly optimized manufacturing networks. Tesla's strategy has been different. Instead of trying to outproduce every competitor immediately, the company has repeatedly focused on redesigning the manufacturing process itself. That philosophy can be seen across multiple areas of its business, from large structural castings that replace dozens of stamped parts, to highly integrated battery packs, and now to dry electrode production. The underlying objective is the same in every case: reduce the number of manufacturing steps, simplify assembly, and lower the total cost of building each vehicle. Why does that matter so much? Because battery cost still represents one of the biggest barriers to making electric vehicles affordable for a larger share of buyers. Even if battery prices continue falling, manufacturers are competing in a market where a difference of only $500 to $1,000 per vehicle can influence consumer demand, profit margins, and pricing strategy. If manufacturing innovations reduce production costs without compromising quality, companies gain far more flexibility than they would through incremental improvements in battery chemistry alone. This also explains why investors increasingly pay attention to factory technology rather than just new vehicle launches. A new model may generate headlines for a few weeks, but a manufacturing breakthrough can influence production for the next 10 or 20 years. Every future factory can incorporate that improvement, multiplying its impact across millions of vehicles. In industries driven by scale, the companies that build products more efficiently often create advantages that become difficult for competitors to overcome. The next stage of the electric vehicle race, therefore, may not be decided by which company introduces the fastest car or the battery with the longest driving range. Those achievements still matter, but they are becoming easier for competitors to match over time. Manufacturing efficiency is different. Once a company develops a production system that consistently delivers lower costs and higher output, rivals cannot copy it overnight. They must redesign equipment, retrain engineers, qualify suppliers, and rebuild entire production lines, a process that can take years. And that is exactly why so many analysts believe the industry's biggest story is no longer happening in the showroom. It's happening inside factories, where the battle has shifted from building better batteries to building them in a fundamentally better way. If that transition accelerates over the next few years, it won't just influence Tesla. It could reshape how the entire global battery industry thinks about manufacturing for decades to come. But there is another reason this story matters, and it has almost nothing to do with batteries themselves. It has to do with time. Most people assume that once an automaker announces a new battery technology, it can simply install it into next year's vehicles. In reality, the timeline is far more complicated. Before a single battery reaches a customer, manufacturers must validate materials, qualify suppliers, test production equipment, certify safety, and prove that the cells can survive thousands of charge and discharge cycles under extreme temperatures. That process can take several years, which is why battery companies are constantly thinking 5 or even 10 years ahead. The factories being designed today are expected to remain productive well into the 2030s, meaning every decision made now could influence millions of vehicles over the next decade. That is why Tesla's manufacturing strategy has attracted so much attention. The company isn't just trying to reduce today's production costs. It is trying to build a manufacturing platform that can continue improving as battery demand grows. Industry forecasts suggest global battery demand could exceed 5 terawatt hours annually before the end of the decade, requiring hundreds of new production lines around the world. Building that much capacity using traditional methods would require enormous investments in equipment, energy infrastructure, and factory space. Even modest improvements in manufacturing efficiency could translate into billions of dollars in long-term savings as new facilities are constructed. Another important factor is energy consumption. Battery factories are among the most energy-intensive manufacturing facilities in the automotive industry. Large drying systems, climate-controlled environments, precision coating equipment, and continuous quality inspection all require substantial electricity. If future production methods reduce the amount of energy needed to manufacture each battery cell, the benefits extend beyond cost alone. Lower energy consumption can improve factory productivity, reduce operating expenses, and make it easier to expand production in regions where electricity infrastructure is more constrained. Supply chain flexibility is another area receiving increasing attention. Over the last several years, manufacturers have experienced disruptions affecting everything from raw materials to shipping and component availability. As a result, many companies are redesigning their production systems to become more resilient. Simplifying manufacturing processes can reduce the number of specialized systems required inside a factory, making future facilities easier to build, operate, and expand. While no single innovation eliminates supply chain challenges, improvements in manufacturing efficiency can help companies adapt more quickly as market conditions change. This is one reason competition has intensified across the entire battery sector. Automakers are no longer evaluating suppliers solely on battery performance. They are also examining production capacity, manufacturing efficiency, long-term scalability, and the ability to support rapidly growing demand. And in other words, the conversation has expanded beyond who builds the best battery to who can reliably build the most batteries at the right cost for the next 10 years. History shows that industrial leadership often changes during moments like these. The companies that dominate one generation of manufacturing are not guaranteed to dominate the next. Every major technological transition creates opportunities for new production methods, new suppliers, and new engineering approaches. Whether dry electrode manufacturing ultimately becomes the industry standard or remains one of several competing solutions, it has already changed the conversation. Instead of accepting traditional battery production as fixed, manufacturers are now questioning nearly every step of the process. And that may be the biggest breakthrough of all. Sometimes the innovation that reshapes an industry isn't a new product that customers can see. It's a manufacturing process hidden behind factory walls, one that quietly lowers costs, improves efficiency, and gives its creator an advantage that becomes visible only years later when everyone else is trying to catch up.